알았으니까 시작합시다. 중학교지? 일단 이거 나온 거 여기까지 만들었네. 설마 1시간 배우는데 다 맞추겠지? 이야, 쫙 틀리네. 멋지게. The atomic orbital of hydrogen, if it has different layers of the atomic orbital, right? S1, 1s, 2s, 2p, and near the sun, there's a high energy there. Then they can exchange the energy with the atom, and then hydrogen can observe the light by jumping to different layer of the orbitals, and that's why we see many peaks, many bands from the sun area. So it's not just a single atomic orbital. 그래도 두 명이나 왔었다. 희망이 있네. 유빈이만 빨리 딱 찍더라. 위치를 보니까 1분 찍는 것 같은데. Okay, so if it is in the stable energy state, so in most of the cases, the atomic orbital environment on Earth, 25 ° 1 atm, is a relatively low energy state. In that case, usually we see 1s state. Okay, but still, if you heat it up, it can go to 2s or 2p, it can jump around. Okay, so this is most common case we see, but that does not mean that it's always there. Okay, it's always a dynamically move up and down. Okay, hydrogen case, usually there's a one electron, or sometimes it can lose that electron and H plus. Sometimes it can take one more electron, H minus it can form, but H2 minus is difficult to get because energetically it's not stable. Okay, the carbon case, it has 6 electrons, and nucleus also has a 6 plus charge. So it has enough energy to collect electrons. 6 electrons there, even though it is a stable status, you know, 1s 2 electron, 2s 2 electron, 2p 2 electrons. It's mixed orbitals. Means in the one atom there are s orbital, p orbitals, they're mixed. In hydrogen case, one electron was jumping up and down usually, but in this case, multiple electrons existed together, occupying the same space. Okay, so that's the state, that's the image we needed to get for atomic orbital. 참 뻔한 것 같은데, 다 알 것 같은데 저렇게 물으니까 뭘 얘기하는 거지? When we said sp3, that the carbon has 2s 2 electron, 2 electron on 2p, but if it is spread out, The paired one is not so stable. One electron jump out. So 3p1s, they make together and then recombine to make a more stable status. That's what we call the orbital, hybrid orbital of sp3. Right? So when you say sp3 for one atom, one carbon in this case, that's only carbon's electrons. Then they can form sp3, new combined recombinated atomic orbital. Still, they didn't meet with another partner. It can meet with another carbon, or it can meet with another hydrogen. Before they meet, that's still carbon's atomic orbital, mixed, but that's only from carbon. Right? 이상해? 다음 문제 풀고 다시 한번 생각해. Okay, now getting close. So this is atomic orbital, but that is a hybrid atomic orbital. Previously I said mixed orbital, that means they just exist together, coexist. They don't interact to each other. S orbital, p orbital in carbon atomic orbital, they don't interact to each other. I taught to you one term to describe that situation. What is that term? They exist together, mathematically they are right angle, they do not interact to each other. What is that? 응? 뭐라고 그랬어? 누가 먼저 얘기했어? 상민이가 먼저 얘기했나? 후배한테 안 보여보자. 이래서 also 뭐나. Also means 딱 각을 지키는 각 잡힌 수직 이런 거고. Also gonal is the angle. So physical, the mathematical meaning is it's 직각 to each other. They exist together, but they do not interact to each other. That's why they can be on the same space. Okay. So mixed orbitals, they do not interact. They are also gonal. That's why they can exist together. But they need to interact. They find the more stable status. That is this hybrid orbital. They interacted and regenerated, recombined, recombinated, and then generate sp3 new directions. Okay. Still, that's atomic orbital. They didn't meet with another atom. If they meet with the other carbon, sp3, they meet together. Right? If they meet with the hydrogen, sp3 meet with another 1s electron. Right? So that's why sp3 itself is still atomic orbital, hybrid orbital. Okay, 109 degree. 야, 조금 틀린 사람 있지만 대부분 다 맞췄네. 숫자에 강해서 좋아. 꼭 빅살이 많으시겠네. 정삼각형이고 120 degree. 오, 생각보다 많이 맞췄는데 좋은데? Y6, I expected there are some 3. sp3, sp2, sp2. Two atomic orbitals meet together, right? And then they form this bond And then this one, same plane. This one, same plane. This one, same plane. At least minimum 6 atoms, they should be on the same plane. Okay? And the angle here is 120 degree. That's why if you draw something like this, I would feel like this. That's not comfortable. Even though you draw by handwriting, try to present most natural structure. Okay? So that's the status here. One. It's a 2 bond, so 1 bond is a 2 electron, 2 bond should be 4 electron, and those 2 bond is not equivalent. 1 bond is a sigma bond, and the other bond is a pi bond, and 2 bond has a different characters. Okay. Carbon-carbon single bond is approximately 80, 90, 100. To make it easy to memorize, let's just say about 100. Carbon-carbon sigma bond. Okay, approximately 100. So pi bond is weaker than sigma bond, and actually that's about the 60, 70. But to make it easy to memorize, about half. Let's just say pi bond, the dissociation energy is half of carbon-carbon sigma bond. 660, the 50 was similar to silicon-silicon bond, right? So that was weak. That's why it was easily broken. That's why it was not chosen to be organic molecule. Okay, sigma bond about 100, pi bond approximately half of that. Okay, easy to memorize. That amount, exact number is not important. Also, depending on the molecule, the value may be a little changed, right? But about what range is good to know. Good to keep. Okay. Oops. Okay. 상민이가 제일 잘했나 봐. Okay. Move on. Okay. The last class we learned up to double bond. So now we move to triple bond. Triple bond. If you draw simple way, we draw this way. 3 bond. But already we know that those 3 does not mean that they are equivalent bonds, right? Then inside there, you can assume there are, now here, the bond is sp character, this color. Means 1s, 1p mean together. When we have sp3, it has a x component, y component, g component. So that's a 3-dimensional. That's why end result is a tetrahedral structure, 3-dimensional, right? sp2, x component, y component is on the same plane, right? That's why the resulting molecular orbital is triangular structure, but that's also on the same plane, right? Now we have 1p and 1s, only 1-dimensional character, px, and then s. So resulting molecular orbital is also 1 to this direction and small tail. The other one go to this direction and small tail. So that's also a linear structure. Angle 180 degree. Makes sense, right? Molecular orbital is a combination of atomic orbital. That's not calculated by Schrödinger equation because it's difficult. Electron motion interact to each other. That's why it's almost impossible to perfectly calculate mathematically. That's why we assume many vectors, and approximately we say atomic orbital, we can linearly recombine. Then original character somehow has the resulting character in the molecular orbital. Okay, that's why one axis of a p orbital, one s character, it makes a linear molecular orbital. Makes sense? So this is a sp orbital, and then it has this can make sigma bond, and then one unparticipated pi electron pg and py is still there as pi electron. They keep perpendicular y component and g component there. Okay. Then if they meet together, so this is what we see from the top. Maybe this is sp green one. sp meet another sp. They make one sigma bond here. And pi electron YG is still there, and then loosely, not strongly, loosely they make this bond. Character of a pi bond is like this, loose bond. So if I take a hands like this is sigma bond, very strong. Okay, pi bond is like this, and then holding loosely. I don't bend too much, then this bond cannot be strong. Okay, that character, now it has a two pi bond, one this way, one this way. So that's triple bonded character. Then, let's just say carbon-carbon single bond, approximately bond dissociation energy 100 kilocalorie per mole, we said. Double bond, maybe 150. Triple bond, approximately 200, we can guess, because it has a two pi bond here. Okay. Even though it has a three bond there, it's not 300 kilocalorie per mole. Two bonds is weaker than the single bond. So this is triple bond character, and this is the summary of that. So let's see some of those numbers. Bond length, carbon-carbon single bond, 1.5 angstrom. Carbon-carbon double bond, maybe a little shorter, it's a little stronger, shorter, double bond here, 1.3. Triple bond, if we keep following this trend, 1.5, 1.3 should be 1.1, but that's a little longer, 1.2. So that range. Atomic distance, atom to atom, approximately 1 angstrom, a little smaller or bigger, 0.1 nanometer, right? So carbon-carbon bond 1.5, double bond 1.3, triple bond 1.2. Energy, carbon-carbon single bond, where is energy? Okay, so to make it easy, kilocalorie per mole. Carbon-carbon double, the single bond approximately 100, double bond approximately 1.5, triple bond approximately 200. Okay. So this is the character, and then we learned about the single bond, double bond, triple bond, basic bond structure in organic molecules. And let's review all together. Ammonia, NH3. Ammonia geometrical structure is like a what shape? You know, your background is not chemistry. Your material science. Okay. Ammonia's the molecular structure. What kind of a shape? NH3. Like this. Okay, ammonia is not planar structure. Ammonia structure is like this. Ammonia has only 3 bonds, but if you look at in the center, it has a 1 pair of a lone pair electron that act as kind of an empty bond. 1 bond, 2 electron. Right? So 2 electron, 2 electron, 2 electron. These 2 electrons, paired electron. Pair means it has its own partner. Right? Paired electron, but it occupies 1 bond space. So this is approximately tetrahedral structure. Not perfectly symmetrical. In this case, the angle, if you look at, original angle should be 109, right? Now it becomes a little smaller, 107. And explanation is these bonds, those electrons are much more concentrated on the bond. but this electron is relatively freer. That's why they can occupy a little more space, and they push this down. That's why this angle becomes a little smaller. Okay, lone pair electron, free electrons, so they occupy a little more space and can push. Okay, now go to, and then if you have, like, instead of a hydrogen, if you add methyl group a little bigger, then even we see the symmetry is a little broken. In this case, this is bigger, so it can push this hydrogen, push it this way. So originally 109, 107, but this is a similar 107. This one is a 110 because it pushed this. Wait a second. Does the match? Originally, the symmetrical ammonia has a 107 degree, right? Now, this one is still similar to 107. This one is a 110. The sum does not match. And the other angle here, this one to this one is also 110, right? Why the angle is not, and sum of the angle is not same? 우리말로 해. 여기가 위로 올라가면 오케이, 뭐 결과적으로는 그런데 보면 앞에 거하고 비교했을 때 comparing to this structure has a little bigger angle because this becomes a little more planar like this. Because this method pushed up, this guy also pushed up this guy too, with its volume here. So originally it was like this, that's why a little smaller angle, but now because of the bulky group, it becomes a little more planar. Okay, that's why the angle is changing. Some of those angle is a little bigger. Maximum angle, of course, 120. If it's a fully planar, there should be some of, it's a fully planar, some of them should be 360 degree, right? So this is still a little dented, but comparing to ammonia, it's a little more planar like this. Okay. So that means this structure of molecules, depending on their shape and also the character of those electrons, they can be a little dynamic, and they push each other to find out its final position, more comfortable position for each one. Okay. Now, water, H2O. What shape do you expect, Yumina? 구분 모양. And in terms of the atomic electron structure, how do you define? It has only 3 atoms. That's why whatever you draw, it could be on the same plane, right? 3 atoms can define one plane. So anyway, we can see only if you look at the nuclear position. So anyway, it's a 구분 모양 like this. But if you count all the electrons, actually it has electron here and here too. So that's also kind of tetrahedral structure and similar to sp3 character. Right? So in this case, now we have 2 lone pair electrons. They occupy more space. Ammonia has a 107 degree. So in water case, that's even one electron pair. They push it further down. It becomes about 105 degree, even further than it. Okay. Here, now if you add one methyl group, now methyl group is pushes this way, so it's a little up now. So this is methanol, and then becomes a little bigger. So memorizing everything is difficult, but it's good to memorize. Ammonia, 107 degree, water 105 degree, perfect tetrahedral structure 109 degree. That much, it's useful information to use as reference. Okay, and then you can think it's difficult to get exact number here, but now we can see originally it should be 105, but somehow this is a little bigger. You push it out, so it becomes a little bigger. Okay, water, chemically speaking, water you can say oxygen hydride or hydrogen oxide, correct? Dihydrogen oxide. Cousin to water, hydrogen sulfide is H2S. H2S, what structure do you expect? Should be like a similar structure like this, like water. Angle wise, water is a 105 degree, right? Sulfur, what do you expect? This angle becomes bigger or smaller? Smaller? Why?
황이 산소보다 더 훨씬 크기가 크기 때문에.
크기가 크기 때문에 that electron up here, that's water is a 1, is that 1s? There's a 2p. The sulfur has a 3p, so that's a bigger, that's why it has an even bigger space they occupy, and it pushes down. Wow, that becomes like a 90-degree range, almost a rectangular structure like this. And 105 becomes even smaller, almost a 90-degree. And then now if we have methyl group there, then it becomes a little open up, 90 to 95. And if you have two of them a little further, 100 like this. Okay, similar trend we can see, right? So again, 109, 107, 105, maybe sulfur, 90 degree. This kind of reference number you can think. Okay, so this is the atomic structure. Now let's try to combine. Now to make the atomic bond into molecular orbital, atomic orbital into molecular orbital, 1s to 1s. Example would be hydrogen molecule. Hydrogen has lowest energy is S and S. They meet together and they can make molecular orbital like this. Mass should be conserved, right? 질량 보존의 법칙. Energy should be conserved. Electron should be conserved. Orbital number should be conserved. We started with the two atomic orbital. They meet together if they make a hybrid orbital, like so-called molecular orbital, then two atomic orbital should make a two molecular orbital. And total energy should be same because energy should be conserved too. That's why if they meet together, they make this bonding orbital. It's more stabilized than this. That's why they go to this. Exactly the same amount of energy stabilized here. Another energy status which has unstabilized up here. Now this is the energy scale. The lower, the more stable. The higher, more energetic. That's why the more unstable. Okay. So in this case, it forms one molecular orbital here, and the other molecular orbital had the formed up here too. So this one is not stable. That's why it's difficult to make a bond. That's why we say this bond is a bonding molecular orbital. Stable molecular orbital. Electron staying molecular orbital. This one is unstable, even though electron can jump up here temporarily, and it can come back very quickly to more stable space. So this bond is also called the anti-bonding molecular orbital. Arbitrarily we gave it the name. Now again, original atomic orbital's character should be reflected in molecular orbitals. So this one has symmetrical structure like this. We just put red color in both. If it's red to red, they have attractive force. It's a little different from electric force, right? Electric force, opposite charge should attract to each other, and same charge should repulse. But electron orbital, we put same character, they interact attractively. Different character, they cancel out or push out. So here, arbitrarily we put red color, and then they meet together, and then one bigger red, then this can be bonding orbital. But we can assume that this can be blue color too. And blue meets with red color, then that's unstable. They cannot make the overlapping, and then that is the resulting molecular orbital, imaginary. And then we can put on the same axis, we make this as unstable molecular orbital. Okay. Now pi bond. Pi bond, now they can meet this way. Red attract to each other, blue attract to each other, and then you can make this is pi bond. Same way, this one can be reverted, and then upper part is blue color, and lower part is red color. Then they cannot make a bond. So this is unstable anti-bonding, pi anti-bond, pi bonding orbital. Okay, move on. Okay, sp3, sp2, that is a hybrid one. In similar way, we can draw red to red, they can make. If it's the opposite direction, blue to red, it may not make. So this is a sigma bond, similar to this bond. Okay. So that is that is kind of a description. Whether that's exactly true or not, approximately that's true, but this is just to help you guys or help us to understand or to persuade ourselves there may be this kind of molecular orbital, and there may be some kind of bonding, anti-bonding, maybe this kind of a character. 95%, 98% experimental can be proven. Always there is 1-2%, something cannot be explained. Means the real nature is a little more complicated, but this is easy way to describe those character of bonding. Okay, this kind of a bonding, what do we call? Covalent bonding. By sharing electron together, and then two atoms, two nucleus can exist in a close distance in 1 angstrom range. Carbon to carbon 1.5, but anyway, that range is kind of moving like this, but they don't go apart. Staying in this range by sharing one pair of electrons together. That's the nature of a chemical bonding. And that bonding, we say, this is covalent bonding. Okay? Covalent bonding, this is most updated version of description using quantum mechanical atomic orbital into molecular orbital. Okay? Now this is organic chemistry, so we may need to learn and also practice how to draw and how to describe organic molecules. Okay? How to draw organic molecule. Let's say this kind of molecule, how many carbon there? 5, how many electrons there? How many the hydrogen there? 12, okay, good. So if you draw this way, then drawing one molecule may take a long time. So we want to make it simpler and faster way. Maybe we can draw this way. So unit by unit, okay, this one, CH3, and like this. Or maybe this one and this one looks like they are symmetrical to each other. Maybe you can combine it together. And then up to here, CH and this one come together and package it together and then put 2. This is the one way too. Still, if you need to draw this way, carbon, 5 carbon atom, the molecule is not so big molecule, it's a relatively quite small molecule. We are handling much bigger molecules. Then if you should draw all the time like that, it's quite cumbersome. So, simplest way we invented is this way. Only the skeleton structure of carbons. So here, 1, 2, 3, 4 carbon. I drew only carbons. Maybe this is the simplest way we can think. Ignore electron, ignore hydrogen. If you don't see anything, then we assume that the position has 3 hydrogen here, 2 hydrogen here, 1 hydrogen here, 3 and 3. So this one is simplest way. If you can think even simpler one, tell me. Maybe that is the simplest way to draw organic molecules. That's something we are going to use from now on. Okay, skeletal structure. Okay. Now, but if they have any kind of a functional group, That's a little different story. Oxygen, nitrogen, if you have a non-carbonic structure, then we need to put those characters here. There is no alphabetical thing, right? So in this case, basic structure of organic molecule is composed of carbon and hydrogen. Now, if you add anything else, then we need to write down. Then that is example of OH, NH2, like this. So if you draw that way, there's a small rules. And if you put this way, we don't put HO because we wanted to show O is connected to carbon. So this is more conceptually more straightforward to understand. Same way. So OH, HO is reversed, but connection-wise, O is connected. O is connected. Same thing. If you want to draw, the others are all carbons. If you need to point out this hydrogen, then sometimes we can put CH3 here too. But here, C is connected to this. If you put on the left side, C is connected to this. This is how this is reverted way, this way. N is the same, H2N, N is connected, N is connected. Now, if this method becomes bigger, this is easy, same way, CH2, CH2. Now here, we don't put H2C. Now it's confusing here, H3C, H2C, and it's a little confusing which hydrogen is belonging to which carbon. So this is a recommended way. If it's bigger than methyl, we put same order. A little confusing, but actually there is no fixed rule. This is just a preference, and just to make it easy to recognize the structure. We don't say, even though you change this CH3 here, we don't say it's wrong, but this is a common way usually we use. Okay? Then try to follow the common way. I think that's the easier way. Now let's think. So if you have your notebook or whatever, you can think how to draw this. You need a little practice. This one you can draw this way. Okay, double bond and single bond. Here, how many rotatable bond here? How many rotatable bonds there? Two. Okay, here is one, here is another one, okay? Two. Actually, this CH, this one is also rotatable, but we don't see the effect. Because hydrogen here, that's we assume that the zero, the dimension, is a very small ball. Then even though we rotate here, we don't see the effect. But if you rotate here, then this CH3 group is moving. So it's like I have a sword, and then I draw like this, then I make some space like this, right? Occupying the space. It's a similar situation of an electron cloud. Electron make it very small. We said the nucleus is 1 femtometer, very small. Electron size is actually difficult to measure. And according to matter wave, Mujilpa, depending on the velocity, speed, the electron behaves smaller and bigger. The faster the size becomes smaller or bigger. Wavelengths of matter wave equal P is on the bottom, P is a momentum is mv, mass is fixed, then that is proportional to velocity. Velocity goes up, then they behave like a smaller particle. Okay, so very fast moving electron behave like very condensed small particle. It's very loose electron, they residing near to nucleus. They becomes very relaxed. So that size is like occupying the atomic size. So they can be femtometer size to nanometer range. Electron behaves like that way. Okay. So in this case, Now, so this one is a similar way. CH3 moving this rotate, then this whole group is rotating, making big cloud. So there is impact of rotation. That's why it's cracked. Okay, one rotative bond, the other rotative bond. Pi bond, usually we assume they are not rotatable because one sigma bond is rotatable, but 5 electron like this, right? They hold to each other, they prevent this rotation. Okay, good. How about this? 6 member ring here and the CH3 group here. Simply withdrawing like this. Quite simple, right? How about this? Benzene ring in the middle, and then one OH group like this. Now, for the functional group, we need to put oxygen and kind of the alcohol there. Okay? So this kind of thing we need to practice. How about the methanol? If you draw the methanol as skeletal structure, 누가 나와서 한번 그려볼래? 누구한테 시켜볼까? 신유. 신유가 가운데 앉아있으니까 오른쪽에 있는 친구를 한번 시켜볼까? 이름은 뭐야? 나와서 한번 그려볼래? 여기 메탈로 한번 그려. 이런 폼으로. 재비다. 아니 이렇게 스켈레톤 폼으로. 메탈 방식을 아는 거지. CH3OH. 오케이, 그거를 이렇게 그리면 다들 꺼내가지고 그려볼래? 내가 지금 항상 보게. 앉아서 보고 있을 일이 아니야. 못 그린 사람도 많은데 그린 사람도 있지만 야, 생각보다 웃기지. 못 그리겠죠? So, okay. So this is the methanol. Funny, right? This is ethanol. And ethane, 2 carbon, this is ethane. How about the methane? 1 carbon. Holy cow, this is methane. Just 1 dot. So 1 dot is difficult to show, so that's why this here is no choice. You can draw like this. This one is also, what is this? This is the 1 line. It's a little too simple, right? So then maybe you can say like this. This one is also methanol. If you don't have other structures, sometimes it looks a little funny, right? So anyway, this is methanol. 1 carbon here. This position is not carbon. Heteroatom is connected. Okay, this is a notation the one we use for organic molecules. You need to practice and then understand, and also can draw and count. If you make a mistake here, then you add 1 more carbon or less carbon. That's critical mistake. That's why you need to have a practice. Okay, this one, now let's think retroway. If you have this kind of molecule, then can you count how many hydrogens are attached to there? Okay, this one, no hydrogen. This one. This carbon, hydrogen number, no hydrogen, because carbon has 4 arms, is all occupied, no hydrogen. This one, 2 hydrogen. This one, 1 hydrogen. This one, 2. Are you sure? Yeah, 2 hydrogen. This one, no hydrogen. This one, 3 hydrogen. This one, 2 hydrogen. This one, 1. This, 0. This one. Okay. So simple, but you need a little practice until you get the use. Okay. So this is the end of chapter 1. So we learned the very basic structure of atomic orbital and then how they can be combined together and kind of things. Okay, and we just finished chapter 1, and we didn't finish yet. I'm going to continue to chapter 2 today. So anyway, the next class is next Thursday, and we finished one chapter. So assignment is Thursday morning. Okay, I put up those assignments on the PLMS. You can download those problems. I usually put 5 or 6 problems, and then solve them by handwriting and put it up before next class. Then you are ready to hear the next class. Okay. Okay, format of the file. Please don't put your number and other things. Just to give your name. That's enough. Okay. And then make the file into PDF file. PDF is a standard printable format. If you put other file format, JPG or HWP, then depending on computer setup, opening up, it looks differently from what you see. To avoid that, this format is invented. Then PDF, any computer open up in the same format. Okay, you draw it, and you can take a picture or scan whatever, and you can convert that into PDF, and just by putting your name, just upload. If you put the number and others, then I should delete and the format every time. Okay, just your full name in Korean, not in English. Okay, so this is chapter 1. Any questions so far for chapter 1? If not, we go to chapter 2. Okay, today we don't have a quiz. Chapter 2, I already dropped the notebook on PLMS, so you can download the tool. Okay, chapter 2 is about covalent bond, polar covalent bond, and acid and base. Something maybe very familiar to you. So far we have learned carbon-carbon bonding. That's the most important bonding in a sense in organic molecules, because organic molecules are composed of carbons, and carbon-carbon connection is the most important bond. True. Carbon and carbon, in principle, they are equivalent. So that covalent bonding, covalent means sharing. So that 2 electrons are shared maybe evenly or equally. But if that bond is connected to carbon-carbon, hydrogen-hydrogen, okay, that's even covalent bonding. But if one of them has a little more attractive for the electrons, now that balance is broken. And charge separation happens. If it was extreme case, one is fully negative charges, one is fully positive charges. That kind of a system we call ions. And that bond we call ionic bond. Typical example we here that we put is sodium chloride. So sodium Na plus is happy enough, hang around in the water alone. Chloride same way, but if you dry them, they come together, and now they make regular structure, and they make a crystal of sodium chloride. And then that bond, crystal means they have some bonding in there. Last time we said, out of 4 forces in nature, molecular level, we count only electromagnetic force. No gravity, no nuclear forces. Then, all the bond characters, basic origin is electric field, electric charges. Covalent binding is a little different, looks like there's no electron distribution. Actually, when we draw Schrödinger equation, we put those electric attraction between nucleus 2 electron, repulsion of electron 2 electron, by just putting some boundary conditions. So we already used electrophilic attraction, the interactions in Schrödinger equation 2. Okay? If it's fully separated, not sharing, usually we draw hard ball. 2 holes do not mix together. One positive, one negative. Electric force wise, they attract to each other and stack. That's ionic bond. Now, seems like there's something in between. they have organic equivalent character. They are sharing that electrons around here. That's not hard ball. It's kind of soft ball. Partially they share some electrons, but electron charge, the charge separation, one part has a little more charges than the other. So partial character of negative charges and the partial positive charges. Partial, when we have learned the mathematics in high school, some small changes, the notation was delta. Delta is a little changes. We have a time t plus delta t, distance added like this. Okay. If this difference is smaller and smaller, so this is large capital delta, small capital delta is delta. Okay. So this means it's even smaller. When we learned about the differentiation, the given case, we needed to think about the limit, the time condition. So we put that kind of things. Small negative, small positive. That means if it's fully moved, then -1 plus 1. Okay. So this is the polar bond character. Now this is defined by these experimentally measured values, so-called electronegativity. Electronegativity is the trend of one atomic nucleus, how strongly they attract electron. That relative tendency, it's not, there's no unit here. Do not confuse this with ionic energy, ionization energy, and electron affinity. Both of them are energy unit. Okay. To remove one electron, how much energy we need to put? By putting one electron, how much energy stabilization is achieved? That's electron affinity. Okay. So those are energy unit, but electronegativity is just a scale, relative scale, and it doesn't have any unit. Now, carbon is the center of organic molecules. Carbon is 2.5. The higher number means it's more electronegative, more attract the electrons. Okay? Then we can see these heteroatoms, nitrogen, oxygen, fluorine. This way, electronegativity becomes bigger and bigger because electron is increasing one by one here, and positive charge is also increasing one by one. And then going this way, the center nucleus is more condensed positive charge there. So that's why they have more attractive forces. Okay, going this way, going down. So this area is what we call metallic. Metallic part, they easily donate or remove their electrons to be stabilized by removing that extra electron, 1 electron, 2 electrons. These guys, they take the electron, and affinity-wise, this is the top. Fluorine is the top, the most electronegative atom, 4.4. Carbon 2.5, and another one we need to keep in mind is hydrogen. Hydrogen 2.1, a little more electropositive. Then CNH bond, which one is more electronegative? Carbon or hydrogen? Carbon is a little more electronegative. So if you draw the carbon and carbon bond equal, carbon and hydrogen bond, electron may be here, we can assume, in the center, 2 electrons. In here, this one is a little more electronegative than hydrogen. That's why electron may be a little more shifted to carbon side, we can imagine. Electron density wise, this is a little more electrons around here. More electron, that's why it becomes delta negative. Okay? Less electron, that's a delta positive. So this character of a bond we call polar covalent bond. Polar, non-polar came from this concept. Now, if you think those connections, carbon to heteroatom, like nitrogen, oxygen, fluorine, and this is electronegative. Now, opposite way is hydrogen or metals, then that's opposite directions. And this notation we put that electron shifting utilizing this arrow with cross here. To make it easy, this is the plus side. This is negative side. Plus here, oops, sorry. This is the plus, this is the minus. Okay, electron is attracted to this way, carbon, oxygen going this way. Carbon, hydrogen going this way. Then let's look at it again. So here, carbon, oxygen going this way, from bottom to top. Metal, carbon going this way. Hydrogen, carbon going this way. How polar it is, that is defined by the difference of these electronegativity values. Electronegativity value-wise, this is 1.0. This is the opposite direction of 1.5. Which one is more polar? This is more polar. This number becomes bigger. That means difference of one atom to the other atom, that difference becomes bigger. That makes this molecule is even more polar. Okay. Here the polar means this pole is one end and the other end. Polar is in Korean, we say 극성. 극성 means 남극, 북극, one end to the other. Polar means it has two different ends. If it's equal, then there is no end. It's just distributed evenly, so non-polar. Okay. Now here, this kind of the charge distribution is one-dimensional on the same line, and that's why it has a two pole, positive pole, negative pole. That's why two pole we call dipole. If it's a four pole, if it's 3 point, tripole, 4 pole, quadrupole. So those numbering system, I made one of the video clip. You want to study sometime soon. So anyway, dipole, two polar stages, one here, one here. Okay, and this dipole can be measured as a unit like this with a d. Dipole moment can be calculated. If this number is becoming bigger and bigger, that's more polar. Okay. Now here water, so oxygen to this way. Forget about these electrons. Now here they are comparing oxygen to hydrogen. Oxygen is more electronegative, that's why going this way. Makes sense, right? Here, carbon to oxygen, then going this way. Nitrogen and hydrogen, nitrogen is more electronegative, so going this way. So this is how we define those dipole moment and polar molecules. If the molecule is very symmetric, if you look at only this half, this electron moving to this way, then we can draw CO2. One dipole moment here, the other dipole moment here. But if you sum it up, it's symmetric to same direction. So this one is total dipole moment is cancelled out, so it becomes 0. Okay, it can be one-dimensional, or it can be three-dimensional like this. This is delta minus, this is delta plus, right? That direction should be clear. Which one has more electron density? But anyway, this is symmetric, and this one is also symmetric. Now, symmetry-wise, this one has what kind of symmetry here? What is the symmetric point? Symmetric element here. Is that meter symmetric or point symmetric? There is a symmetric point in the middle here. Through this point, everything is symmetric to each other. So that's why all dipole moment is cancelled out because of the symmetry. This one, 6 membered ring, And this is we need to learn something more. We need to learn resonance, and then we can come back to this. Anyway, benzene is also symmetric. These kind of things we can call. These symmetric molecules can be considered as non-polar molecule, even though they have some partial local polarity, but altogether, because of symmetry, that the polarity is cancelled out. But all other cases, if they have non-symmetry, biggest one, let's just say sodium chloride, fully one, fully minus one. And if they come together, then their dipole moment is much bigger than partial charges. Makes sense, right? So water can be referenced. Water is 1.85, and non-polar is 0. There's no minus value. Okay, formal charge. Now, if you draw the molecules, and this way, and sometimes we put minus and plus like this. How do we define that? And let's check one by one. Carbon. Carbon, original carbon atom, it has 4 electrons on the valence shell. Means we ignore the 1s. We only count 2s because 1s is a very the beneath the surface. They do not interact much with outside. So we just count the main the interacting one outside the electrons, 4 electrons. Originally they had 4. And utilizing this 4, usually they make a 4 bond. Once they make the 4 bond, seems like if this is a covalent binding, I donate 1 electron. Hydrogen donate 1 electron. And then they make 1 bond. Then if you compare these two, originally I had 4. Later, we share these electron pairs one by one. And then anyway, half of them is my part. I invested 1 electron. Then half of those bond, totally 8 electrons, but half of them is mine. So this is the original point and this is the ending point. If you take this out, the 4 minus 4, 0. So there is no charge changes for carbon. Originally I had 4 electrons, and ending positions, 8 electrons, but half. Then divided by 2, then this one is shared by this, then we can assume that half of the 1 bond is my electron. That's why there is no charge changes, 4 to 4 electrons. How about the nitrogen? Nitrogen originally 5 electrons. And then 3 of them, they participated in the bonding. 2 of them still I keep it. Then when you count, originally 5, and the ending position, I have 3 bond. 3 bond, 6 electron, but only half of them is mine. So 3 electron here, and lone pair electron is anyway is mine. Totally 5, no changes. So that's why this nitrogen is also 0. Most of the cases, if it is a fair covalent bonding, no changes. That's easy. So if you summarize the general rule, original number of electron and the minus bonding divided by into 2 bonding electrons, or maybe bonding number is the same way. 1 bond is 2 electrons, so bond number or bonding electron minus 2, anyway same. And then also the non-bonding electron, if we take this out, then that is the formal charge. Practice. So here the oxygen. If you look at the oxygen originally it had 6 electrons. Now it has 1 bond and it has 3 pairs of lone pair electrons. Then ending position, 1 bond, 1 electron. And 3 pairs of electron, 6 electron, totally 7. Originally I started, oxygen started with 6 electron, but it ended up with 7 electron. Then 1 extra electron. 1 extra electron minus 1. Electron is negatively charged. So calculation wise, original number of 6. And then ending number, 1 bond and 3 pairs of electrons, minus 1. Let's calculate the sulfur. Sulfur, oxygen, same family. Right? Then oxygen have a 6 electron. Sulfur has how many electrons? 6 electrons. Same way, just the outer shell, but same other configuration. Now 6 electron originally. Now it has 3 bond and 1 pair of lone pair electron. 3 bond, 3 electrons. 1 pair of lone pair electron, 2 electrons. Totally 5. Sulfur started with 6 electron, but ending position is 5 electron. Result is plus 1. 1 electron missing. 1 electron missing means 1 negative charge is removed, then net 1 positive charges. So that's why original 6 minus ending position of the electron number here, then make a plus 1. So after you draw this line, if it's carbon make a 4 bond, usually 0, easy. Oxygen make 2 bond, it's 0, easy. But oxygen make 1 bond, now we have a little trouble. It doesn't match up those electron sharing the balance. And oxygen has a 3 bond, or sulfur has a 3 bond, that's also trouble. To correct that strange situation, we put this kind of charges to make our heart feeling easier. Oxygen 2 bond, nitrogen 3 bond, carbon 4 bond, then everything's okay. We don't need to put the charges. But if that is going a little strange configuration, then we need to think some electron is moved from 1 extra going to oxygen. 1 electron was here, but that is actually given to oxygen. Kind of situation occurs. So this is what we call formal charge. Not always true. That's why formal charge, 형식 전하, 형식을 맞춘 전하, 마음이 편하기 위해서 저렇게 그려야 말이 되니까. 때로는 딱 저대로 안 되지만 저렇다고 가정하고 그리는 게 formal charge. 공식은 이런 공식을 따르고. Original number of electrons and then real situation electron number. Then we can get these positive and negative numbers. Okay? This is the formal charge. Practice. Carbon radical. Carbon is originally 4 electron. And if you make a 4 bond, it should be happy, but it has a 3 bond here. And but 1 bond, 1 electron, it's still there. Radical is not stable, is not happy, but charge-wise, 1 electron, 1, 2, 3 bond, 4 electron, no changes. Okay? So charge-wise, neutral, 0. Make sense? Carbon can make a 4 bond, but 1, I still keep as a 1 electron. 0 charges. Carbon plus here, that means originally 4 electron, 3 bond, and then this electron is removed. Carbon positive charges, we call carbocation. Carbocation, this is a real charges, formal charge, but actually this is a plus 1. 1 electron is removed. Then we can think opposite case too, right? Carboanion. Carbocation, carboanion. Radical is neutral, but it can take 1 more electron. Anyway, radical is unstable. If it has a partner that's more stable, partner or just leave alone. Remove that electron. Remove carbocation. Take 1 more electron, carboanion. Okay. Ending position is 5 electrons. That's why 1 more negative charge. Nitrogen. Nitrogen is happy with the 3 bond, but now it has a 4 bond. That means 1 bond, this lone pair electron fully donate those the 2 electrons to make 1 bond. And the result, 1, 2, 3, 4 electrons for this. 1 electron missing. That's why 1 plus. If a nitrogen has a 4 bond, that has 1 plus formal charges. Opposite way, give up one bond but take one more electron, then this is N minus. Original one is amine. This positive one we call ammonium, and this negative one, anybody knows how to call? Anybody knows? Very funny. This is called as amide. Amide is actually we use for different the term too. Peptide bond is amide bond, but this one is also called as amide, N minus. Oxygen, 2 bond is natural. If you make a 3 bond, that means one pair electron is donated to the bonding. So it gave up 1 electron. That's why it's a positive charge. Then opposite direction is give up 1 bond but take up that electron. Then this one is O minus situations. Okay. Sulfur is exactly same to oxygen. 3 bond positive charges, 1 bond 1 negative charges. So this phosphorus is similar to nitrogen. So same way, 4 bond make it positive charges. So this is a summary of these formal charges. If you look at here, then calculation, well, in the beginning you may need to follow this formula, but after some time, if you look at it, you can easily think N 4 bond positive charges, O 1 bond negative charges, O 3 bond positive charges. Carbon 3 bond either plus or minus, it can go either way. Carbon case. Either it can give up, it can take 1 more electron. Okay, so this is commonly we can see in organic molecules. Okay, stop to here. Any question? 자, 민욱이는 다음 수업을 못 오는데 다음 수업에 해당하는 게 챕터 2니까 챕터 2에서 문제를 배워서 푸는 걸로. 민욱이하고 디스커션을 하다 보니까 결석을 하면 어떻게 해야 수업을 묻히자고 따라올 수 있을까. 내 경험에 제가 교수된 지 20몇 년 됐는데 해보니까 수업을 빼먹으면 살아남지를 못해. 그래서 는 가능하면 수업을 꼭 들어오기를 원하는데 꼭 수업을 빠져야 되는 상황이 생기면 교과서 문제를 푸는데 얼마큼 풀게 할까? 그것도 생각해봤는데 민욱이하고 얘기하다 보니까 수업을 한 번 빼먹으면 2번 한다고 쳐, 한 챕터를. 그러면 그 챕터에 있는 문제를 한 절반 정도 골라서 풀기. 2번 다 빼먹어야 되는 상황이면 한 챕터를 다 풀기. 근데 2번 다 빼먹는 건 권하지 않아. 2번 빼먹고 살아남는 학생을 내가 본 적이 없어. 그래서 최대한 웬만큼 아프더라도 수업은 빠지지 않도록 하고 룰은 그렇게 정하는 걸로 민욱이하고 얘기하다 보니까. 오케이? 수업 여기까지.